Hi, so welcome back to the next lecture series on uh, metric space and topology. So remember in previous couple of videos we are discussing with compactness of metric spaces, and there we have tried to find out the relation between the sequentially compact and also Bolzano-Weier's property and the compactness of a topological space, and we have proved these two relations, that Bolzano-Weier's property if and only if sequentially compact, and compactness in place Bolzano-Weier's property, and sequentially compact to compactness. This particular circle was done like this one. This was done. Now, just to in order to make the circle complete from another direction, we just need to prove that sequentially compact meets the compactness property. Okay, and to prove that we need something called positive debug number associated to any open cover of a topological space, and something called epsilon net. Okay, so these two things were there, and in the last lecture we have proved up to that every every sequentially compact space has a positive Debug number. Okay, so there was the proof. I think you have I believe that you have gone through all these topics. So now let us move on and let us complete the circuit. So the theorem is that sequentially compactness implies compact set. Okay, so suppose x comma d, this is sequentially compact, then x and with the induced topology tau d, this is compact as topological space. Okay, so suppose we consider that as it is sequentially compact, so we need to show that every open cover has a finite subcover. So we can assume that gi, this is an open cover for x. Okay, then since it is sequentially compact, so this particular open cover, this must have a positive Lebesgue number. Okay, so let us consider that let A be the positive Lebesgue number. Okay, and again we have said that any sequentially compact metric space is totally bounded, right? So this is totally bounded means for every epsilon it has an epsilon net. So it has for each epsilon and then 0. So we call epsilon to be as a by 3. Okay, so if we consider epsilon to be as a by 3, so we must have a by 3 net, right? So that means I get some, let's say, a particular set capital A, which is basically consisted of, let's say, okay, not 8 to make it convenient. So let us take A1 up to AN. Okay, this is be the A by 3 net. Alright, so as it is A by 3 net, so that means union of all n belongs to natural number, the ball centered at AI with the radius A3, this is basically X. Okay. So as it is X, so let us give it as condition 1. Now for any small x belongs to B of, let's say, any age I am taking, any particular age AI, or let's call it as AI1. If we take small x belongs to this, so the distance between AI1 comma x is strictly less than a by 3. Okay. Now if we take any another element, let's say small y itself, also from here, so I will get d of ai1 and y strictly than a by 3. So what is the distance between x and y? So is less or equals distance of ai1 comma x plus the distance between ai1 comma y by triangular property, right, or triangular inequality. So I get d of xy is strictly less than 2a by 3. Okay, so that means basically what I'm getting, that the distance of let's say the diameter of this particular ball, this is basically less or equals 2a by 3, because for any two element taking from this one, their maximum distance, I mean their distance is basically 2a by 3. So I may say that this is basically the upper bound of all the dxy's where x and y are coming from this ball, right? So the diameter is basically diameter is the supremum of all such d of xy's where x and y coming from this ball. So that's why this one is less or equal to 2a by 3. I don't know, the diameter may be 2a by 3 itself. Okay, because the supremum one need not to be in the particular set, supreme may be outside of the set itself. So it is enough to take diameter of is basically of a by 3 with ai1, it is less than this. So now note it is less than a, small a itself, right? So as it is less than small a, so that means this particular ball b a by 3 of ai1, this is inside at least one GIs, right? So at least let's say it is one inside GI1, and thus it is true for each AIs. So hence each, or let's say for each, let's say for each I belongs to 1 to n, we have the ball radius at ai with a by 3, it is inside gi, right? That means this entire union small I equals 1 to n b of ai a by 3, it is inside the union of all small I equals 1 to n gi, and this is itself x. So we can enoughly take that x equals union of all I equals 1 to n gi's. Okay, so this will act as a finite subcover. So that means that this particular collection, this is finite subcover for x. All right, so this is how one can construct the, one can have the proof. So that means basically x is compact. So you note that we have used the property once we have used the property of being totally bounded and having a positive Lebesgue number. Okay, so these two properties are the main key ideas, and we have discussed these things in previous video. So that's why I stopped there. So I think now it is very easy to follow the proof, and in fact right now the circuit is going to be complete. Let me make it here again, that suppose we have the Bolzano stress property. So from here I have sequentially compact, from here I have compact as topological space. So from here is there, this particular is there, this is there, and this particular is there. All right, so this entire circuit is done. So that's why this means this particular time commutes. Okay, so this is how one can construct this circuit. All right, now what is the usefulness of the compact metric space in topology? So suppose this particular theorem is going to be very helpful in real analysis itself to see that whether any function is uniformly continuous or not. So suppose f is a function from x comma d1 to y comma d2, let's say this is continuous function. Okay, so is it always true that, so that means it may be uniformly continuous or may not be. I'm sorry, not this one, let me mention it with this one. So this may be uniformly continuous or may not be, right? But once we impose the criteria that x comma d, this one is compact, then it is of course uniformly continuous. So that means the theorem basically says that it's continuous, let x comma d1 is compact, then f is uniformly continuous. Okay, just to recall that what is uniformly continuous. Uniformly continuous means in real analysis, let me explain because it is easy to visualize. That suppose you have a curve like this. This is my curve f of, let's say, R itself. F is a mapping from R to R. Okay, so continuity means if you have any certain x naught here, I must get, here it is f of x naught, let's say, so if you consider any epsilon neighborhood around this, this means epsilon neighborhood, I must get a certain delta neighborhood around this. Okay, such that whenever I take any point in between these, it will be inside this particular one. Okay, inside this region. All right, so this is how one can construct the map, and I mean one can achieve the property of continuous function. But uniformly continuous means the choice of delta, this particular delta neighborhood, it doesn't depend on the point of x naught. Okay, so that means if we change the epsilon from here to here, it will change the delta itself, but it will change with respect to epsilon only, but not with it will be not related to x naught. For example, if x equals x, this is infinitely continuous. But what about if x equals 1 by x, where it is not equal to 0? I mean in fact we are defining f1, let's say it is f1 is from r minus singleton 0 to r. This is not infinitely continuous. Okay, all right. So but in case of once you have in arbitrary topology, I mean now you can impose the property of uniformly continuity in case of a continuous function in any two arbitrary metric spaces, right? So this theorem says that if you have any compact metric space, then any continuous function from that compact metric space to another metric space will be always uniformly continuous. So what's the problem? Okay, yeah. So first the proof. Let us erase it. Yeah. So let's see what's the proof. So suppose we have f comma x comma d1 2y comma d2 is continuous, right? And so we need to show that if you choose any epsilon means real number larger than 0, you should have some delta which is not dependent on the choice of particular point x0. So let us fix a point x0 belongs to capital X. Okay, be any point. So of course we know that f of x0 belongs to y. This is codomain set. So as it is continuous, so f inverse b epsilon by 2 f of x0, this is subset of x and this is open in X. Okay, so now this is my arbitrarily chosen. And this one we need to prove and we need to find. Okay, it's a suitable delta that we need to find. Now for every x0, of course x0 belongs to f inverse b epsilon by 2 f of x0, right? So we can construct an open curve just gathering all these f inverse together. So in fact G is collection of all collection of all f inverse b epsilon by 2 f of x0, or let's say f of x, where small x belongs to capital X. This one is an open cover for X. Okay, so as it is open cover, so this must have a positive Lebesgue number because it is a compact metric space. So this must have a positive Lebesgue number. Let delta naught be the positive Lebesgue number. So it is a delta naught. So this one I have got, and this positive delta naught doesn't depend on choice of x0, right? Because it is uniform for any particular chosen x0, whatever I choose. So now let us put delta to be as delta naught. So now my question is that will this be enough to verify the continuity property of f? Let's have a check. So let's suppose small x1 belongs to capital X, any another point. So let the distance between x comma x1 strictly less than delta. Yes, with delta means delta naught. So as it is a positive Lebesgue number, we may consider that a to be as these two elements x comma x1. Okay, so then of course this one is subset of certain b epsilon by 2 of f of x. Let's say f of x2, right? So that means the distance between oh, not this one, yeah, sorry, f inverse of this, because the open cover is basically consist of all the set of this form, right? So for some x2 may be different. So that means that the f of x1, f of x this belongs to b epsilon by 2 f of x2, and f of x1, this belongs to b epsilon by 2 f of x2. So that means the distance between fx and f of x1 is less or equals this distance between f of x comma f of x2 plus the distance between f of x f of x1 comma f of x2. So it is distance between f of x comma f of x1 strictly less than epsilon by 2 plus epsilon by 2. So means distance between f of x comma f of x1 epsilon. Alright, so that means f is continuous in x. This property is verified with chosen delta. So this choice of delta, this does not depend on x naught, any point chosen. So that's why the delta doesn't depend on x. So this not depending on the chosen point, and hence f is uniformly continuous. Okay, so this is the beauty of this compactness of metric spaces. I said that as metric space in except metrizable topological space, there is a very fundamental opportunity for, or let's say feasibility for us to having a metric that induces a topology. So that's why it is very convenient to work with metrizable topological spaces once it is compact. Then only it satisfies these very beautiful properties. But it may not be helpful for in general topological space, because in general topological space we don't have the notion of positive Deborah numbers or something like that, right? All right. Now we have remembered that in case of real analysis, we said of that the set of rational numbers and set of irrational numbers is a countably dense. In fact, set of irrational numbers are countably dense, but irrational numbers are uncountably dense. So why did he say this? So that means that suppose you have any real line like this, and you take any two particular elements, let's say R1 and R2. In between to this, there are infinitely many rational numbers, right? Or let's say if we take any two rational numbers, there are infinitely many rational numbers. So that means how small you make that interval, you must get infinitely many rational numbers out there. All right. So that is basically the general notion of dense property. So let's say the definition. What is dense subset? So dense subset means suppose x comma tau is a topological space, then let's say a subset of x, this is said to be dense if a closure equal to x. Okay, and what is separable metric space? So let's say x comma tau is a topological space. This is said to be separable if x has a countable dense set. It's a countable dense subset. Okay, and what is second countable? Second countable means it is a countable basis. Okay, all right. So there is a small remark, let's say. It's observation. So this observation says that any separable metric space is second countable. This is as topological space. Okay. So suppose we consider that x comma d, this is separable metric space. Okay. So this separable metric space is a countable in subset. So there exists A equals AI. This I belongs to different natural numbers. Okay. I'm taking it to be as let's say any countable means maybe finite itself. Okay. This is countable. So it is a separable metric space, so it must have it is a countable and dense subset. Okay. So that means X must be a closure. So my claim is that it is a second countable, means it has a countable basis. So let us consider that B to be as set of all the ball, it is generated by each AI and with radius small q, where AI belongs to capital A and Q belongs to rational numbers. Okay. So first of all, this is open set. This is a collection of open sets. But to prove that it is, in fact, it is by it is also countable. Why? Because it is basically there is a bijection with A cross Q, right? Because you see that the choices for the centers are finite and the choices for radius, these are also finite. That's why it is it is clear that they are finitely countably, not finite, it's countable. A is countable, Q is countable. The choice of all such open sets, the entire choice is basically countable. That's why this entire collection is countable. So it is nothing big issue to prove that it's countable. So countable is done. But the thing is that it has to be basis, that is we need to show. So to prove it is basis, let us take any open set. U is open in X, of course in tau d, where tau d is a topology induced by the metric D, right? So let us take small x belongs to capital V. So there exists small r naught belongs to real number which is strictly larger than 0, such that B of the ball centered at X and radius with r naught is inside U. Okay. Now there are two choices for small x. I have chosen small x to be arbitrary. So small x may be in A or may not be. So let us assume that small x belongs to A. Because why it is true? Because small x belongs to capital X, and that means small x must belongs to a closure. Because we have assumed that x A to be as separable, so it is countable in subspace of X. So X has to be in A. So either X to be in A or may not be. Once it is not in A, so that means X must be derived set of A. Okay. So if X is in, let's say, capital A, then we are done. There is nothing to prove that, because we may assume that any smaller subset, any smaller element from there. So then we may assume that, suppose this is my set A and there is my small x, and here is the ball. Here is the ball, okay, which is inside capital A. So now, as this one is smaller, R0 is any real number, so I can take any small q belongs to q such that small q less than R0, right? So that means now I can choose this one, this particular ball. So now the ball with radius small q with x, this has to be inside the ball radius with R0 with x, and this has to be in u. So this particular ball is inside u, right? This is fine. But so if it is in S, then we are done. But if it is in derived set of A, so that means for any, so that means this particular ball B R not at X, this must intersect with A, but which is not same as small x. So that means there exists some small A belongs to capital A such that small a belongs to B R not x and small a is not equals x. So that means what? If we have a ball like this which is centered with small x, radius with R naught, and if we have any point here, it's small a, right? Okay, not R naught, let us make it very small. So not R naught, let's say R naught by 3. Yeah, make it very small, because we have this particular ball, like means basically we have a larger ball like this which is centered at small x. This is my R naught. I'm making it very small like this. Of course we could work with this as well, but it is convenient for us to, for the calculation, to consider R naught by 3 itself. Okay, so let us, this is by R naught by 3. Okay, now here is R naught by 3, and let us, somewhere this is another ball which is 2 R naught by 3, this one. Which is, this one is 2 R naught by 3. So this particular one from here to here is 2 R naught by 3. So that means I have R naught by, that means I have here R naught by 3 and here I have 2 R naught by 3, right? So in between I have a real number, of course rational number smaller. So that means there exists, oh let's say it is Q naught. So there exists certain Q naught belongs to capital X, belongs to Q, such that Q naught is R naught by 3 strictly less than Q naught less than 2 R naught by 3 less than R naught, right? So now what about small x? So the distance between small x and A, this was less than r0 by 3. So this is inside somewhere here, the point, this particular one, right? This is my small x. Not yeah, it is not small a, it is small a. I'm sorry. So somewhere this is the black dot is small x. Okay, so that means it is strictly less than 2 r0 by 3 itself, right? In fact, this is less than r. This is 2 r0 by 3. So that means where is the ball 2 r0? R is basically somewhere like there. This ball. No, it is very white color. So let us take it this one. I think this will be visible for us properly. So that means this particular one. So here this is my small q0. Okay, so of course small x belongs to B q0 of A. Okay, now if we take any element which is small u belongs to B q0 of A, be any other small u, be any element. So what is the distance between u and A? So this is less than q0, of course less than 200 by 3, right? So what is the distance between u and x? So this is less than u and x less or equal to distance between x and A plus the distance between u and A, and this is x and A is less or less strictly less than r0 by 3, and this is okay. Oh, I'm sorry, we have to take this element from small x, sorry, small x itself, yeah, right? So now the distance between small x and A. So that means the ball is basically of the form here like this. So the ball is basically like this. I think it is not visible. Let us take it as black. Okay, this will exceed small x, exceeds from r0 by 3 because smaller is larger than r0 by 3. It should not be there. So it is r0 by 3 plus with 200 by 3. Means it is strictly less than r0. This is how we have made this distance very small. So that means the u must belongs to B of, yeah, this r0 u comma A. Yeah, now it is fine. U comma x. Yeah, so u must belongs to B of r0 of u, and this is inside capital U. So that means B of q0 of x, this is inside U basically. Okay, so that means I can get an open set from this particular collection, capital B, this one, such that this in any sets of this form is inside U for any open set capital U. So that means it is basically works as a basic open set for the collection of all for this second separable metric space. Okay, so that means in case of metric space, separability in base, second countability. All right, but what about the converse statement? So conversely also true. That means once you have any second countable topological space, then we can say that it is separable. So to prove that condition, let us consider that any second countable metric space. So x comma this is second countable, means it is a countable basis, right? It's countable basis. Now let us construct capital S to be as small gi, I belongs to capital N, where each gi, these are distinct and chosen from distinct gi. So that means the construction is the following, that for every small I belongs to capital N, we have gi belongs to capital Gi, and for any I is not equal to j, I have gi, the chosen set capital Gi, is not same as capital Gj. That means we have G1, G2 and so on like this, right? So I will choose exactly one element from each of these GIs. I will not repeat any particular J once more. Alright, so this particular set is of course countable. Because it is union of some certain countable collection. Okay, so it is countable. In fact, we can construct phi from S to not S, it is set of all natural number n to B itself, and another map. This is, it is bijective by definition of B, because they assume that B is countable. So B phi 1 is from B to S, such that any particular gi maps to the representative of that is of course bijective. That means phi 1 composed phi, this is from natural number n to S, this is bijective. So that means as it is bijective, so this collection S is countable. Alright, now what we need to show that this particular set S, this is S is dense in X. So dense means S closure equal to capital X. So let any small x belongs to capital X minus capital S. It is not in capital S, so for any epsilon means real number less than 0, consider B epsilon of x which is inside capital X. This is open set, right? And as we have chosen this to be a basis for the for the topological space, a topology induced by the metric D, so this must contain certain gi. Okay, so that means from this particular collection, let's say gi1, so that means from this particular collection X, there is small gi1, this belongs to B epsilon of X, and of course gi1 is not same as X because we have chosen small x which is outside of capital X. So that means this B epsilon of X, this intersects with capital S but this intersection doesn't contain the chosen element small x, so this is not phi. That means capital S is dense in X. Okay, that means S closure, this is capital X. That means count in case of metric space we have countability, second countability if and only if separable. Okay, so this much is related to the compact metric space so far, and in the next series we'll study some more properties of compact space and then move to separatedness. Okay, so please go through all the lecture series, all the lecture topics we have discussed so far, and in the next class onwards we'll meet with some new more topic. Okay, thank you very much for your patience.